Is the following statement going to be true, that for all integers a, b, and c, if a divides b and a divides c, then a does divide b squared minus 2bc plus c squared, or, of course, this is going to be the same as saying b minus c all squared, right? So, is this going to be true? I think so, because I've already proven that the similar identity of addition is true. So I'm thinking if you just add a minus, it should also be true. But let's just think of some examples to verify this. Let's just think of one example, because this is a pretty lengthy problem to solve, or at least with examples it would be to compute. So let's take 2 divides 2 and 2 divides 4. So we're then asking ourselves, is it true that 2 divides 2 squared plus 2 times 2 times 4 plus 4 squared, or not plus, we're dealing with a minus now. Well, let's have a look at this. Can we factor a 2 out of this? We probably can if we just simply expand this to look like 2 times 2 minus 2 times 2 times 4. I'm actually going to use brackets here. I like the look of those much more. Plus 4 times 4. And you should be able to see, of course, you can factor a 2 out of this 4, 2 out of here, and a 2 out of here. So this is the same as saying 2 divides 2, huge bracket, times 2 minus 2 times 4 plus 2 times 4. So it's looking like this statement is going to be true. Let's just verify that we are computing this correctly. So because this is the same as saying b minus c all squared, we're just going to quickly look at that. We're going to say this is the same as asking, does 2 divide 2 minus 4 squared, or does 2 in fact divide minus 2 squared, which is going to be 4, and of course that's true because that's what we started with. Is this going to equal to, well, take a step back, gone a little too far ahead. This is going to be the same as asking 4 is a multiple of 2, or 4 can be written as 2 times some integer m, where m here has to be 2. So because here we've written 2 times some integer probably, we have to make sure that this is equal to 2. So this is asking 2 minus 8 plus 8 is in fact going to equal to 2. So it's looking like for this example it's true, so it's probably going to be true for a lot of other examples where a divides b and a divides c. So let's go ahead and try and prove this statement. Okay, so how do we start our for all proof? We always start our for all proofs with let. We say let a, b, and c be integers such that a divides b and a divides c and a cannot equal 0. Once again, if you don't know why I say this, please go back and watch my earlier divisibility proofs. I explain quite well why this condition must be true. Next, we probably want to explain what we mean for a to divide b and a to divide c. Well, it means that then b can be written as a multiple of a, or b can be written as a multiplied by some integer k, and c can be written as some a multiplied by some other integer. We'll call this one j. Fantastic. Of course, now that we've introduced k and j, and unlike a, b, and c, we haven't defined them, we have to define them. So we say where k and j are going to be integers. Okay, I had to sneeze pretty bad. Fantastic. Now that we've defined everything we can, we just have to check that this in fact can be written as a multiple of a, where a is multiplied by something in a huge bracket, where this, whatever's in this bracket, must be overall an integer. Let's start with what we have on the right hand side. So we can say next b squared minus 2bc plus c squared. Now note, it's not very useful to say this is the same as b minus c all squared, because when we plug our definitions of b and c, we're saying ak minus aj all squared, and then you can't really factor an a out here, so you're going to have to expand it anyway to get it in this form. So we're just going to go straight from here and plug in what our definitions of b and c are. So let's go ahead and do that. Okay, there we go. We can definitely factor an a out of all of these, I'm thinking, because these are squared. If you can't quite see why we can do that, let me quickly just show this a little more explicitly, because it's the same as saying a times k times a times k minus 2 times a times k times a times g plus a times g times a times g. And of course, now you can see we can factor an a out of all of these. So this is the same as saying a multiplied by, now I am going to go a step back. So I am going to actually get rid of this middle step. This was just to show you more explicitly that it does allow us to factor an a out. So we can say this is the same as saying a k squared minus 2k ag plus ag squared, right? I think that's correct. Yep, that should be correct. Fantastic. We've now shown that it is 2 multiplied by something in a huge bracket. Just notice that whatever's in this bracket is going to be an integer because everything here is an integer, either multiplied, divided, subtracted, or not divided, forget about division. Multiplied, added, or subtracted, which is still going to make it an integer. So we just have to explicitly state where ak squared minus 2kag plus ag squared is an integer. So we can say b squared minus 2bc plus c squared is a multiple of a given it's equal to a multiplied by ak squared minus 2kag plus ag squared. You don't really have to say the given part, given it's equal to yada yada. You can just immediately jump from this to, so a divides b squared minus 2bc plus c squared. And then you can add another thing saying by definition of divisibility. I'm not going to be that extra. Actually, you know what? I will be. I'll say by definition of divisibility. Let me quickly just highlight what you don't really need to say, but I'm saying just to be super explicit. You do not have to say this part and this part. So just these two parts underlined in blue. But there we go. We have now proven that this statement is in fact true.